Welcome back.
Hi everybody, welcome back.
We have done with chapter P. We are ready to start chapter 1.
Yep, so this is the first chapter that's really going to dive into pre-calc stuff. A lot of it you have heard before, but maybe not in the same way, maybe not this. It's very vocabulary intensive.
Very vocabulary
So if you take a look, there are 8 learning targets for today, and this is only the first half.
Yeah, there's actually 14 total
14.
for 1.2. Okay?
Alrighty?
You can read them.
Okay.
Function definitions. Just out of curiosity, what the heck is a function? Well, last chapter we had you write y as a function of x. And in Algebra 1, what do we call a function? We called it a function if every y value or every input
Has one output.
Not y value, x value. Every input had one and only one output.
Correct.
So every x value that you plug in can only give you one y value when you take it out.
Correct.
Okay? The official definition of a function is a function from a set D to a set R is a rule that assigns a unique element in R to each element in D. What do R and D stand for?
Domain
or D and R?
and range.
Domain and range. So if we take something from the domain, it maps to the range, and that's all we have to worry about. You know what a function is. We just need you to be able to look at some data, look at a graph, and determine whether or not it's a function or not. We're not going to actually quiz you on, please write the definition of a function.
The nice part about this is it's a good review of domain and range, and if what we found in the last few years teaching is that you can't have enough practice domain and range.
Not ever, never, never enough, okay? So first of all, let's talk about domain and range. Domain's the input or the x's, okay?
Correct.
So the domain can be written, if we continue, this is just a set of numbers, that's all this is, and domain is not spelled with an M anywhere in it. So we'll write it as a set. The domain is all the inputs, -3, 4, and 2, and the anal retentive math part of me wants to write them in numerical order. So we'll go -3, 2, 4.
This is usually where students say, if we don't do that, is it wrong? Okay, just do it, and then we don't have to talk about it. Put it in order.
All right, the range is the y values, or the outputs. If you put in -3, you get out a 0. So the range is going to be the 0, the 2, and the -6. And again, in numerical order, that's -6, 0, and 2. Okay? So the question is this relation, by the way, a relation is just any set of ordered pairs, but is it a function? So does every input have one and only one output?
Yes.
And yes, it is. So yes,
It is a function.
it's a function. Okay? All right, how about the next one? We have 4 points this time. We have 4, -2, 4, 2, 9, -3, -9, -3. So
You
the
should say that again
domain.
faster.
We got sold. We have a domain of 4. We have another domain of 4. We have an x value here of 9 and -9. And -9 is smaller than both of those two. So let's try writing that one first, shall we? It's -9, +4, +9.
So, Mr. Leckie, even though there's only there's 2 4s there that were the same, we only have to list it one time?
Well, we got to list it once.
Okay.
Okay. The range then is all the outputs, the y values. And what do we have here? We have a -2, a 2, a -3, and another -3.
So again, -3.
-3 first, -2, +2.
And we don't have to duplicate.
Is this a function?
No.
Why not?
Because the input 4, you look at the order pairs that start with a 4 and the x value, has 2 different y values.
Okay, so we're going to write no,
In highlighter.
preferably not in a highlighted mode. No, since the input of 4 has 2 different outputs. Okay?
And even better if you say not a function, since that works too.
Not a function.
Thank you.
Better.
It's beautiful.
Yes.
Got a couple more examples.
Okay.
So this time we're giving you some pictures. How
Yeah.
does that change how we look at it?
Well, I don't like that color.
What?
The definition of a function can be looked at a picture with the vertical line test.
Okay.
The x value, wherever you are, can only have one y value.
Okay.
So what we do is we take a vertical line, we draw it straight up and down. That's vertical.
Well, vertical line has the same x and a lot of different y
So
values.
this line represents all the possible y values. All we got to do is drag it around our picture. Does our graph hit our vertical line anytime more than once?
Yes.
That means that every time that happens, that x value had, or that input had 2 different outputs.
Okay.
So not a function. And the reason is because it fails, we call the vertical line test. So we're going to abbreviate that VLT, if that's okay with you.
Okay, so touching the line more than once is bad.
Touching line more than once is bad. So here we go. We're going to drag it across our function.
No.
Does the line ever hit the graph more than once?
No.
Nope. So we're going to say yes, it's a function. And the reason?
Because it passes the vertical line.
It passes the vertical line test.
Very
And this
well.
thing is not really quite oriented very well.
Is that gonna bother me?
Probably. Okay. All right. Let's continue with domain and range.
Okay.
Specifically domain. 'Cause
Domain
there's
becomes very, very important.
very, but we don't want to have to draw a picture or list all the points every time we want to do something.
We don't, and sometimes we're not allowed to use our graphing calculator either.
Ooh,
So
that
there's a couple
sucks.
of handy dandy rules.
Three of
okay?
them.
And I kind of treat domain like you are innocent until you are proven guilty. You are in the domain until you can show me a reason why you can't be in the domain or why a number can't be in the domain.
Fair enough.
Okay? So we usually start with all real numbers, or from negative infinity to positive infinity. But there are three rules that we need to be careful of. We may not, ever, 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 square root a negative.
Not,
Doesn't work.
not with real numbers, we can't.
Okay? We may not divide by 0.
Bad things
Okay?
happen.
You can't have some sort of expression and divide by 0. That's bad. We also, and this is the one people forget, we may not, inside the input of the logarithm, we may never use a 0 or negatives.
So positive numbers only.
Positive numbers only on a logarithm.
Now we will spend an entire section on logarithms later in chapter 3, won't we?
We will. And next couple of classes, we'll also talk about the pictures that go with logarithms and square roots and things like that. So right now we're just doing this what we
Three
call
rules.
algebraically. Okay?
Keep them in mind.
Don't square root a negative. Do not divide by 0. And don't do either one for a logarithm.
Perfect.
Okay, so let's try some examples. So without using our graphing calculator, of course,
So we only have 3 rules to deal with.
and we're only dealing with domain right now.
Okay.
Okay.
Range is much easier when you know what the function looks like.
It is. It is very visually. Okay, so we have y equals the log of x. So our function is a logarithm.
So this is like rule 3 from earlier.
This is rule 3. What can we not do to a logarithm?
We cannot have negatives and we cannot have zeros, so the inside of the logarithm function, which is in this case is x, has to be greater than 0.
It does. So
Not
how do we
equal to.
say greater than 0 in interval notation?
Well, from 0 to infinity, and it's not including 0 or infinity, so it's open on both ends.
That's it, you're done.
Piece of cake.
Okay. Second problem, we have a fraction. Warning, warning, fractions.
No dividing by 0.
No dividing
Does
by
it matter
0.
what the top is right now?
Nope.
Not at all. So we just set the bottom not equal to 0 and solve for x.
Correct. So how do we solve this? We subtract 3 on both sides. X cannot equal a 3.
So that's our
again,
domain.
we're talking all real numbers. Think of a number line, and you plucked out a negative 3.
So how do we write that with interval notation?
Well, we're going to start at negative infinity, and we're going to go to a negative 3, but we cannot include either one, because this is an
Okay.
infinity, and that's a negative 3, which we just said we couldn't be. But then
That
we
was
need to
really
be on the other side of negative 3, and we need to go to a positive infinity.
Perfect.
Okay, letter C. So letter C's got a couple of things going on here. It's got a square root and it's got a fraction. So I'm going to go ahead and move that over so I can have a little more room here.
Need more room.
Need more room. So this time we have a fraction, but we're going to have to deal with the numerator this time. Why
Okay,
is
so
this
last time we didn't
different?
have to worry about it because there was no square root or logarithm in the numerator.
Correct,
Okay,
correct. So
all right.
the numerator last time kind of was irrelevant. But watch out for those 3 rules again. All right, now, what do we know about square roots?
Well, we can't have negatives, so we have to have x plus 2, the inside, be greater than or equal to 0. It's okay to have zeros inside of a square root.
It is, because the
as
square
long
root
as
of
it's
0
not in
is
the
0.
denominator.
Right, right. The square root of 0 is just 0. A lot of students ask me that. Okay.
We'll
so
solve for x.
solve for x, we get x is greater than or equal to negative 2. Okay,
So that's
so
part of our domain right now.
we'll just think about that for a second and let that rest,
Let it
And let's-
sink in.
marinate. Let's
Marinate.
let's look at the denominator.
So we don't want the denominator to be 0.
That's
So
not
I'm
allowed.
getting this urge to factor this denominator.
Okay, so let's go ahead and factor that. Hopefully you can do that really quickly.
And if you need to worry about the box for yourself, go ahead. But, you know, that's what it's going to come out to be.
Okay, so again, we have 2 different factors here. So that means that x minus 4 cannot be a 0, and x plus 3 cannot be a 0.
Oh, so x cannot equal 4, and x cannot equal negative 3.
Correct.
All right, so we have to make sure we include all of these pieces. The red has 2 problem numbers we can't use. But remember, up above, we had that greater than or equal to negative 2. Now, this would be a lot easier if you just kind
Draw
of
a picture.
draw a picture and a number line.
It gets a little confusing.
This is not your answer. It's just a way to kind of do some scratch paper and figure this out. So let's,
Okay.
negative 3, we're not going to use.
We're not allowed to use negative 3.
We're never going to use 4.
We're never going to use 4. It was over here somewhere,
And negative 2's in the middle there somewhere.
closer to the negative 3.
And we're going to we can use negative 2, but only numbers bigger than that. But we can't use 4. So in this problem, we can't use numbers less than negative 2 anyway. So does it really matter that we can't use negative 3?
No, but we had to go through the algebra to see that.
All right, so we
Okay.
really just want to describe the interval that's bigger than negative 2, including negative 2, but not including 4. So we'll stop at 4 and put an open parentheses, and then go union 4 to infinity, and we're done. That's our domain. But you see how the picture was much more helpful? Is that an English phrase?
It was more helpful with all the different pieces. Once you start to get more than one piece, definitely go ahead and draw a picture.
All right, let's continue.
All right, so we've talked about functions, we've talked about domains. Let's talk about a new word for you maybe is continuity. Continuous. What does that mean, Mr. Lucky?
Well, non-technical terms, it just means you can draw the entire picture without ever lifting your pencil.
You can. Not that you did, but you can.
Yes.
All right, so if it's not continuous, this is an absolute. You are either continuous or you are
Not.
discontinuous or not continuous. Okay, so first thing we want to figure out is it continuous or not? And then if it's not continuous, if it's discontinuous, we've got some different types of discontinuity that we're going to talk about. One is removable, the other is not removable.
And there's really only one kind of removable, so everything else is non-removable. We'll
Pretty
talk about
much.
it in a moment.
Okay, so letter A, we've got this picture. So let me go ahead and see if I can draw this picture. Whoop, right there.
What is that thing?
That's an open circle.
It's like a hole.
Like, yeah.
Somebody poked a hole through the function. Now it's no fair drawing around the hole and to keep going. Whenever you have a hole in the function, you're missing a point, so you cannot draw it without lifting your pencil.
So that would mean it's discontinuous.
Discontinuous. And a non-removable discontinuity and a removable,
Hold on.
spelling mistakes.
Hold
Okay,
on.
removable discontinuities first. A hole is the only removable discontinuity because you can fix it with one point.
Correct.
You can either define or redefine one single point. That's the official definition of removable. A hole, you could just replace it. Or if the point was above it or below it and missing that spot, you could fix it by moving one single point, and therefore it would make it removable. So the only type of removable discontinuity is when you have a little hole in the middle of a function. Okay?
In fact, we'll call that a hole.
We're going to have fancy names and we'll have names that people understand.
Again, vocabulary, lots of vocabulary. So again, if it is removable, that's an A. You can make it continuous by,
Defining or redefining one point.
I was just going to say plugging in the point, but
Oh,
there's the calculus instructor in him.
there you go.
Redefining. See, now I can't spell. 1 point.
Okay.
Okay.
Everything else is non-removable if it's not continuous or discontinuous.
Okay, so letter B, let me see if we got this straight. Let's go ahead and try to graph it. We go
What
up
is that
here.
dotted line
Oh
there?
my goodness, that's a vertical asymptote.
Oh, I've seen those before.
You should have seen those before, or else you don't belong in pre-calculus. Sorry. Okay?
All right. So,
So-
vertical asymptotes are not continuous there.
They're not continuous.
So what? Since the hole is the only kind of removable one, this supposed to be a non-removable
This
one.
is non-removable.
And again, to be fancy definition-wise, you can't fix a vertical asymptote with one point. Okay, you just can't.
So that makes it non-removable.
You got to fix it with a lot of figuring out ways to connect them. It just doesn't work. All right. So next.
Okay, letter C. Oh, again.
Oh, we have a
Over
hole at
here.
the end of one, but then we have a dot at the bottom, but I can't fix that with one point anyway.
Yeah,
So
because there's all this stuff in the middle that's missing.
yeah, I'd have to kind of connect them, and that would move lots of points. So this is actually called a jump discontinuity, but it is a non-removable discontinuity as well. Okay, it is discontinuous,
Oops. Non.
non-removable. Its unofficial name is a jump. You can jump up or jump down, but it's not just a single hole.
Okay, and it's not an asymptote because the curve is not getting closer and closer and closer to it, which is what happens with an asymptote. Okay, so letter D. Oh my goodness, I'm getting so tired with all these words. Oh look,
Hey, look, that's continuous.
that's continuous.
You drew the whole thing. Don't you wish they were all like that?
I do. No, I don't actually. Then it wouldn't be any fun if you didn't have all these cool graphs.
All right. Well, let's keep going.
Okay,
All right. Increasing, decreasing. What's increasing mean?
going up.
Going up. So we read this graph. How do we read a graph when we talk about going up?
We read a graph from left to right.
All right. So when we're reading it from left to right, those are x values, aren't they?
Yes, they are.
So when we want to talk about increasing and decreasing, the biggest thing people mess up here is that they don't use the right numbers. So we want to make sure that when you talk about increasing and decreasing, they are intervals on the x-axis. They are x values that we're talking about. The words increasing, decreasing are telling us if the graph is going up or down. That takes care of the y values.
Okay,
We want to go left to right.
so what could we be? We could be going up, we could be going down, and we could be constant.
Constant. So here's the easiest way to do
Of
this.
course, he's got a cool picture.
We got a little guy, and he's going to go from left to right. Did he go up or down?
He went down.
All right, if he jumps up here, that's a non-removable discontinuity.
Correct.
Then he's going this way. Did he go up or down?
He stayed the same.
He stayed the same. Then there's this removable discontinuity.
Right.
And then he goes like this. Is he going up or down?
He went up.
He went up, so he's increasing. But then there's this vertical asymptote, so it doesn't count. We
So
got to
now
start
he
over
falls
here.
off.
Yeah, he falls over, and then he's going to go this way. He's going up again, right?
Okay, so
So-
increasing.
When is he increasing? Well, we're going to abbreviate it this way. He's increasing.
Now, can we assume that these are going by the scales 1 here?
Yes. Let's
Okay.
go 1, 2, 3, 4, if it makes you
Okay,
feel better.
so he's increasing from 2, but I cannot include the 2,
2.
to 3, but I cannot include the 3 either because that was an asymptote.
Yep.
And then again on the other side of 3 to 4,
So we go from 3 to 4, and we
but I
don't.
can include 4.
We include 4. The technical definitions of increasing and decreasing means takes 2 points, and as long as the left point's bigger than the right point, it's increasing there. So we're going to include 4. All right.
And basically you can kind of cheat and just look at the picture. Is it closed or not closed?
Yeah.
Okay,
How about when is it decreasing, or when is this guy going down? Well, the only time he went down was in this first interval here.
right, so that was 0 to 1.
That was
We're
0 to
gonna
1, so
include the
include 0. And 1 was
Open.
open, so it wasn't included in that interval at all. So
Okay.
we're there.
And then we have constant.
Constant, and the only time it's constant is when the graph is flat, horizontal.
So that was from 1 to 2.
And that was from 1 to 2. Okay, we can include 1, but we can't include 2.
Correct.
All right, piece of cake. Just remember, everybody knows going increasing or decreasing, what it means. What you got to remember is which values to use, and that's what you're
For
going
your
to have to
answer.
practice.
You want to
okay?
get the right answer by giving us X values.
All right. All right, what about boundedness?
Well, boundedness is probably a new term for you, but there's 3 kinds of boundedness. There's bounded below, bounded above, and bounded. So let's go through these definitions for you.
All right, so bounded below
Means-
ooh, fancy you.
That there is a y value smaller than every other y value on the function.
So can I draw a picture of this real quick?
Please.
So this would be something simple like maybe even a parabola going up.
Okay?
It's bounded below because there's something that's lower than all
Means
of
it
it.
has a bottom.
It could also mean like a exponential function that comes down and never actually gets to the bottom number,
Correct.
but it's bounded below.
So there's some sort of floor that you can't pass beneath. Is kind of what you're thinking.
Yep.
Okay, bounded above. Thank you.
Hey,
Go.
there it is.
There it goes.
It's just the other way. We need a y value bigger than everything else on the function.
Okay?
So we could just turn those 2 pictures upside down, or we'll draw them again. We got another idea of we could have a function that went like this, where it had some bound above that it never reached. Or it could just be as simple as an upside down parabola,
It never goes above that
never
height.
went above a certain height.
Okay? All right.
How about bounded?
Bounded is simply the other 2 combined.
Yeah, you got to be below and above. Now this is where it gets confusing, because if you say it's bounded, you're saying there is a highest and a lowest like fence to this. The function's always going to be stuck between
those two
two.
values.
Doesn't actually have to hit them. In fact, it could look like this, where you had a horizontal asymptote here and here, and it kind of goes like this, where it never actually hits either one of the bounds. Or it could be like a sine and cosine function where
Just bounces back and
it
forth.
actually
never
hits
goes
the
above.
highest and lowest points, but is bounded between -1 and 1.
Okay?
So understand the difference. You're going to basically be just drawing pictures and figuring out if it's bounded below
Or if we
above.
give you a picture, you tell us which it is.
Sure.
Okay.
Okay, piece of cake.
Next, vocabulary.
All
Local and
right.
extrema, local and absolute extrema. Okay, now extrema is just a way, but first of all, that's plural. Okay, one extreme
Extremum.
value, and that's just simply saying maximums and minimums. You've been doing this since algebra 2.
Yeah,
Okay.
just for fun, for you vocabulary nuts out there. Extremum would be one.
Very nice. Or one extreme value, same thing. Okay, including maximums and minimums. So again, local, you could also use the word relative. And again, this could be if you came from FST or if you came from Algebra 2, but it all means the same thing, okay? You have to write this one in.
Okay.
Extrema, remember, are y values.
Y values, don't get them confused
Okay.
with increasing, decreasing.
So increasing, decreasing x values, extrema are y values that are bigger or smaller than. Well, if it's local, it's all the other y values that are close by. Okay?
So the Y values close by.
Close by, nearby, around you.
Close. And why would it be close, like really close by, okay?
Yeah.
All right, how about an absolute extrema?
Absolute is like it's it. Okay? It is the maximum or the minimum. Okay? And again, they are y values. So they're bigger or smaller than all the other y values on the function. Okay? And again, we're specific to what's on the function.
Okay, so we're going to label these real quick. And when we read the directions, it says label f of a through f of e, because those are actual y values.
Correct.
They're not the a's, the b's, the c's, the d's, the e's. Those are x values.
Yes, that would be increasing, decreasing intervals if we needed those.
So what we're doing is we're labeling this point right here is f of a.
Correct.
So what is that?
Well, f of A looks like it's smaller than anything else in the picture, it must be the absolute minimum.
Absolute.
So even though the directions are going to say label the extrema, you need to tell us, is it a maximum or a minimum?
And whether it's absolute or relative.
Correct.
Or local. I don't care which. Now, we can go ahead and abbreviate this absolute minimum, if that's okay with you.
That's
All right?
fabulous.
All right, so let's try f of c's. Is it the next point from left to right here?
Okay, well, it's definitely higher than f of a was, but it's not the highest point on the graph. So
Nope.
let's call that a relative maximum.
Relative. We're
Yep.
going to abbreviate that
We can abbreviate
REL.
that. And max.
All right.
Okay,
Let's
next
keep
point.
going. How about this point? F of D.
F of D. Well, it's lower than the last one, but it's not as low as the blue dot.
And it's lower than all the points close to it.
It's kind of like the bottom of a little bowl.
When you do the relative, you don't have to go very far. You just look at what's really, really close by. And since all the points in right here, that's the lowest point in that little bitty interval, this is a relative min. All right, how about F of E?
F of E. Well, that's that spike-looking thing up there. Okay, and again, that's higher than all the points nearby.
It's the
but
big
it's also
dog.
the highest of the whole graph. So that would be an absolute maximum.
And that leaves us with F of B.
Totally out of order.
Hey, it's left to right endpoints.
Again, it's lower than the ones nearby
Yep,
it.
there's nothing to the right of it, so when the function's going down towards it, so this is a relative minimum.
All right,
We got that?
we got it. Next,
Woohoo. All
more
right.
terminology. Symmetry.
Last thing for the day here.
Okay.
Whew.
Well, symmetry deals with things looking the same on both sides.
Did you
right?
want to draw some of these?
Not really.
Okay.
You go right ahead.
All right. So we have three types.
We do.
Two of them are really important, even and odd.
Absolutely.
Symmetry with respect to the y-axis is going to be an even function, and this is where we're going to pick up the next lesson from.
Right.
But for today, we're just going to look at pictures and numbers. The algebraic part of it is a proving part, and we're going to deal with that in the next lesson. So graphically, what does that mean? Well, it means if we have a function that looks, I don't know, kind of like this. Let's just make it go like that.
Okay.
All right. If
With
I want it
respect
to
to
be
the y-axis.
symmetric about the y-axis, that means like the y-axis is my mirror.
Okay.
So I could literally just kind of go, whoop,
I see.
and pretend like that's
So-
exactly the same on both sides of the y-axis.
We could fold it in half on the y-axis and the two halves would match.
And it's exactly the same.
Okay, so could I go a little further to say if there was a dot right here at, do you want numbers or letters?
I don't care.
At AB, there would be a matching dot over here, but it's no longer AB.
It's on the other side of the y-axis, so it would be negative a, but it's the same height, so it's the same y value of b.
Okay,
Okay?
you like that?
And that's really what we're going to do when we talk about numeric.
Okay,
We'll use some function notation just so you can get used to it. So
Okay.
if, let's say f of, what do you want to call this point?
how about 5, 0?
How about f of 5 equals 0? That would be like this point right here.
Okay,
Pretend, okay?
Okay.
If f of 5 equals 0 is on the graph, or the function, then
it has to have a match on the other side. So
Yes.
how about f of negative 5?
then f of negative 5 also has to equal 0.
Very good.
Okay.
So let's go to algebra and do this with letters.
So the algebra is the same idea, and it's especially important if you look back at this picture. What we're going to do when we get to algebraic ideas is we're going to plug in a negative x. So f of negative x is always going to equal the same y value as f of x.
Okay.
And that's our algebraic
And you
definition.
can see that in the numbers right there because the zeros were also equal.
Okay, this is going to be really, really important for next class.
Important enough to memorize if you've never seen it before.
Start now. Okay.
Start now.
Next one.
Okay, what if it's odd?
Like us? Oh, sorry. How about like me? All right. Odd functions are symmetric with respect to the origin. Now this
Odd
is
origin. Odd
when you're
origin.
symmetric about a point. It's like you could.
You're not flipping anymore.
No, you're actually you're flipping over an x and a y axis. is
Yeah,
the
or
other
you're
ones.
rotating.
You're
That's the
spinning it
definition of
around.
a rotation
Yeah.
from geometry.
Okay. So what we're going to have is if we had a graphical picture of this. Let's go ahead and go through the origin because most of our odd functions will go through. Not all of them, but most of them. We'll go through the origin because that's what it's going to be symmetrical to. So if we had this function look like this.
Okay.
If it's going to be symmetric to the origin, it's going to have to look basically like a mirror image going
That's beautiful.
flipped left and upside down.
Now you see why I made him draw it. We talk about F, A, and B, the point AB. Okay, it's going to have a matching point right about there.
But against opposite A, because it's on the other side of the y-axis, but it's also going to be the opposite B, because it got flipped over the x-axis.
Okay, so So that's where that flip and flip happens.
Flip, flip. So again, these are functions when we're talking about them. So if, let's go f of, I don't know, how about
4.
4 equal 3 is on the graph, then what other function value is going to be on the
How
graph?
about f of negative 4?
Then f of negative 4
Would have to equal negative
will
3.
have to equal negative
So
3.
notice the y's are opposites. The x's are opposites and the y's are opposites. That should help us with our algebraic definition, right?
All right, so if we plugged in a negative x algebraically,
We have to
we
get a
should
negative
get
y.
the
How do we
exact
write a negative
opposite
y?
of f of x.
Okay,
And
opposite
again,
of f of x.
that's going to be our definition of an odd function.
Memorize it.
Okay. Now for the last one, it actually turns out not to be a function,
But it's still some symmetry.
but there's some symmetry involved. You're correct. So how about symmetric about the x-axis? So if we had a picture and we had this picture going like this, again,
Okay?
what would it look like if we were symmetric about the x-axis?
But the x, you have to flip it down this time.
So it would go like this.
Correct.
Well, that's pretty cool.
And it's not a function because it doesn't pass the vertical line test that we talked
Yes.
about already today. However, there is symmetry there. So numerically, if you have a dot, I like my dots.
You go right ahead with your dots.
Again, if you have AB on the graph, then down here, you
You
would
actually
have,
end up with a negative b, and if you notice, that's the same input with two different outputs.
which is what makes it fail the vertical line test.
Correct. So how are we going to write this numerically then?
Well, numerically, let's say this was the ordered pair 2, 3, okay? So if we have the ordered pair 2, 3 on the graph, then we also have the ordered pair 2, negative 3.
Okay.
The problem is when we come to algebraically. Algebraically needs function notation. It's not a function.
Yeah, notice we couldn't even write the numeric version the same way we did the last one, so that algebraic column was probably just copied there because we liked the idea of.
Well, because we want to talk about the fact you can do it.
All right. I think
All right.
that'll do it for today.
That'll do it for today. So we've talked about what's a function, domain and range, increasing, decreasing,
Boundedness.
boundedness, extrema,
Extrema.
maximums and mins. We've talked about symmetry. Anything else?
Lots of stuff.
Continuity.
Continuity. Almost
Okay.
have to look back at all the notes to remember everything we've talked about.
So if we have to look, you should probably look too. Maybe make yourself some note cards and